Assalamualaikum warahmatullahi wabarakatuh. Today, we will present about the relationship between students' age and the average daily AI tools usage using least square solution and best fit curve. Before we start, may I introduce our team members. First, MIRZATUL SAFEAHANIE binti MUHAMAD HISHAM. Second presenter is SYAMIMI ALEA binti BADRUL. And the third presenter is IZZATI SHUHADA binti HAMSIROZZAMAN. Okay, now we go to the introduction. This study focuses on examining the relationship between students' age and average daily AI tool usage. A sample of 20 individuals was selected from the dataset for analysis. Independent variable X, which is age, and dependent variable Y is average daily AI tool usage. The objective of this study is to determine whether students' age has a significant influence on average daily use of AI tools. Let's start with our first model, the linear approach. We are using the equation y equals to a plus bx, which is x is student's age and y is average daily AI tools usage. Our goal is to find the best fit curve by solving the intercept a and the slope b. To do this, the data were first expressed in metric form as m multiply v equal to y, where m is the design metric containing the age value and v is contain the regression coefficient. Y is the vector of daily AI tools usage. The normal equation used to obtain the least square solution is m transpose multiply m multiply v equals to m transpose multiply y. Substitute the data in the normal equation, and by solving the equation using m transpose m inverse multiply m transpose y, the estimate coefficient are obtained, and then we get the best fit regression line. Furthermore, to find error vector, we use y minus mv formula, and the norm e we get 7.027167590. Next, this graph shows the best fit linear regression line for the relationship between student age X and daily AI tool usage Y. The line slope downward from left to right, indicating a negative relationship between the two variables. This means that as students' age increases, their daily AI tools usage tends to decrease slightly. The second graph shows the residuals error vectors of the regression model. A residual is the difference between the actual AI tools usage and the predicted AI tools usage from the regression equation. The points are scattered around the horizontal line at 0, with some residual above and some below 0. This indicates the model sometimes overestimates and sometimes underestimates the actual AI tools usage, since the residual appear randomly distributed around 0 and do not form a clear pattern. The linear regression model provides a reasonable fit the data.
So, moving on to quadratic model, our quadratic model takes the form of y equals to a plus bx plus cx squared, where a, b, and c are the unknown coefficients that we need to determine, and our y is the average daily AI tool usage, and our x is the student's age. So, to fit this model, we first construct the design matrix M, where each row corresponds to one data point. So, for the first column, we use the value of 1, which represents the constant coefficient of a. And for the second column, we use the value of x, which represents the linear term associated with coefficient b. For the third column, we use x squared, which represents the quadratic term associated with coefficient c. So, by using this design matrix, we can form the normal equation, which is m transpose m, and we have the coefficient vector containing the unknown coefficients a, b, and c. On the right hand side, we can see that the matrix M transpose M contains sum of power of X, while the matrix M transpose Y contains the interaction between the observed values and the predictor variable. So, the first entry represents the sum of all observed values, and the second entry represents the sum of X multiplied by Y, which is the linear interaction. And lastly, the third entry represents the sum of X squared multiplied by Y, which is the quadratic interaction. So, by solving this equation, we can determine the values of A, B, and C required for the quadratic model. Next, we calculate the least square solution using the formula, which is V equals to inverse of M transpose M multiplied with M transpose Y. The least squares method finds the optimal values of the coefficients by minimizing the sum of squared differences between the observed data and the fitted curve. So, after we compute the inverse of M transpose M and multiplying it by M transpose Y, we will obtain the coefficient vector of V, and we will get our value of A, B, and C. And then we will substitute these coefficients into the quadratic model that will give us the best fit quadratic curve as shown. So this equation will represent the quadratic function that best fits the given data according to the least square criterion. After we obtain the quadratic model, we will evaluate how well it fits the data. So to do this, we compute the error vector denoted by A by using the formula E equals to Y minus MV. Here, Y represents the vector of observed values, while MV represents the predicted values generated by the quadratic model. So the difference between these two vectors will give the residual error for each data point. The resulting error vector shows how far each prediction is from the actual observed value. So to quantify the overall fitting error, we calculate the norm of the error vector shown as magnitude of E. This value measures the total deviation between the observed data and the fitted quadratic curve. So, a smaller error norm will indicate a better fit because the predicted values are closer to the actual observation. Since our error magnitude obtained is approximately 2.8552, we can conclude that the quadratic model provides a reasonably good fit to the data. So moving on to the first graph, this graph shows the observed data together with the best fit quadratic curve obtained using the least square method. The horizontal axis represents students' age, while the vertical axis represents average daily AI usage. The blue points are the observed data, and the red curve represents the quadratic model. We can see that the curve follows the general trend of the data reasonably well. And for the second graph, this graph shows the residual errors against student age. The residuals are scattered around zero without any obvious pattern, indicating that the quadratic model provides a reasonable fit to the observed data. Therefore, both graphs suggest that the quadratic model is suitable for representing the relationship between students' age and the average daily AI usage.
Next, we move to the cubic model. We use the general equation for cubic model, which is y equal to a plus bx plus cx squared plus dx cubed. So the matrix representation of the above system is by the formula mv equal to y. For the M matrix, the first column are always constant, which is 1, and the second column is x value, the third column is x square value, and the fourth column is x cube value, and times with v and equal to y. Y is our y value from the data. Next, we move to the normal equation, which is m transpose times with m times with v equal to m transpose times with y. So we will solve for v to find the least square solution, which we will use formula m transpose m inverse times with m transpose y. So the best fit cubic curve is y equal to negative 814.11437.1413884 plus 105.1117522078006x minus 4.48799081402137x squared and plus 0.0635270564835858x cubed. Then we calculate the error vector E, which is equal to y minus mv star. V star is the value that we just got from the calculation before this. Then for the error magnitude, we got 2.7099170239341057.2. In the left picture is the graph best fit curve against its observed data. The curve follows the general trend of the data, where the AI tool usage increases at first, reaches a maximum point and then decreases slightly. Although the model captures the overall pattern, the data points are quite scattered around the curve, indicating that each alone may not fully explain the variation in daily AI tool usage. For the next graph is the graph of the best error vector against X values. This graph shows the residual or prediction errors of the cubic model. The residuals are randomly scattered above and below the zero line without forming a clear pattern. This indicates that the cubic model is suitable for representing the relationship between age and daily AI tool usage. However, some larger residual values can still be observed, which means that there are certain data points that are not fitted very closely by the model. The new model has the highest error magnitude, while the cubic model has the lowest error magnitude. So the best fit curve that gives the best approximation is from cubic model because it has the lowest error magnitude compared to the other model.